Now, before we dive into this, I want to sort of set the stage and explain how we're going to describe this. So we're going to talk about potassium first. We're going to talk about its chemical force, which is its concentration gradient. Then we're going to add on its electrical force. And then we're going to look at how both forces are moving potassium. And think about how the overall direction of potassium, even though forces are acting in different directions. We're going to do the same thing for sodium. We're going to talk about its chemical force, i.e. its gradient. Then we're going to add on its electrical force, which is its, because it's charged, right? It's going to have electrical force as well. And then we're going to put both of those together and talk about its ECDF, its electrochemical driving force. And then we're going to combine both ions, and that is how we will arrive at our resting membrane potential. So we're really going to break it down force by force, ion by ion, and then put everything together at the end. All right. So let's start with potassium. And again, the reason that we're looking at potassium and sodium is they are the most influential ions. There are other ions involved, other ions moving across the membrane, but sodium and potassium are the most influential ions. The other thing we want to understand is that we're going to think about this hypothetically, right? We're going to consider a cell hypothetically that is only permeable to potassium. We know that that doesn't exist in our body. We know that our cells are moving multiple ions. But for the sake of simplicity and really kind of zoning in on potassium's movement, we're going to consider this hypothetical cell. So we have a cell only permeable to potassium, and that's going to help us describe the forces that are acting on potassium. Let's start with its chemical driving force. Because we have potassium ions, more of a concentration inside the cell, the concentration gradient for potassium is out of the cell. Higher concentration inside the cell, lower concentration outside the cell. And so potassium's chemical driving force is in a direction that is out of the cell, which is passively or spontaneously. Okay. Now, as potassium starts to move outside of the cell or diffuse outside of the cell passively, it's going to leave behind the unopposed negative charge of the organic anions that were inside, right? I'm going to go back here quickly just to highlight that. So we talk about the balancing, right? Positive being balanced by negative inside the cell, positive being balanced by negative outside the cell as well. So as potassium moves outside of the cell, there's this unopposed negative charge that's left behind inside the cell. So the inside of the cell becomes more negative. All right. So that's the chemical force. That's one part of the equation. Now we can introduce the electrical driving force. And based on what we described earlier about the electrical driving force, it is based on the charge on the particle in question and the polarity of the cell. So because we now have an unopposed negative charge and the inside of the cell becomes more negative, and potassium is a positively charged ion, now we have an electrical force pulling it back in the opposite direction. Okay, the positively charged ion is attracted to the negatively charged environment inside the cell. So as we can see here, we have this scenario where a chemical force wants to move potassium out of the cell, and electrical force wants to move potassium back into the cell. So now we have forces that are in the opposite direction, but they're not equal. So now we have to think about the greater force, okay? Okay, so now we're going to see that the ions are going to move until they're at equilibrium. So now the forces are equal, right? Now the forces are equal. So now we have potassium's equilibrium potential. And we described this concept before as well. When an ion's electrical force is equal and opposite to its chemical force, the ion is said to be at equilibrium. And if we were to stick a voltmeter into this neuron, at this state of being at equilibrium, the reading that we would get is negative 94, which means that potassium's equilibrium potential is negative 94. Okay, another way to say that, when the membrane potential is at negative 94, potassium is at equilibrium. okay? So that is the two movements for potassium. All right. Let's think about the same set of events, but for sodium. We're going to think about a hypothetical cell only permeable to sodium, and we're going to consider its electrical force and its chemical force, and then combine those to see how both forces are acting. We also want to remind ourselves here about the balancing of negative and positive. Outside the cell, sodium is being balanced or opposed by chloride, which is negative, and then we describe what happened with that same balance inside the cell. So let's begin with sodium's chemical driving force based upon where it is at a higher concentration, which is outside of the cell. And just to refresh ourselves, this is owed to the sodium-potassium pump, which is pumping sodium out. So there's a higher concentration of sodium outside the cell. Now, because of that, sodium wants to spontaneously diffuse into the cell according to that concentration gradient. So the chemical driving force on sodium wants to move it inside of the cell. And as we can see, that is going to leave behind an unopposed negative charge because chloride is no longer going to be countered by that positive charge. So as sodium diffuses into the cell, it's going to leave behind a more negative environment outside the cell, okay? And initially, that is going to pull sodium back out, okay? That's going to attempt to pull sodium back out. So sodium has an electrical force moving it into the cell based on the concentration gradient. And then initially it has, excuse me, that was a chemical force moving it into the cell. And then initially it has an electrical force because we now have more negative environment outside the cell that wants to pull it back to the negative environment. Okay. Then the ions will continue to move until sodium is at equilibrium. And when sodium arrives at its equilibrium, the membrane potential value at that time is positive 60 millivolts. So that is to say, when the membrane potential gets to positive 60, sodium's electrical force and chemical force are equal and opposite, and it is at equilibrium. Okay. Remember, we described that these equilibrium potential values are unique for each ion. So each ion will be at home, so to speak, or comfortable or at equilibrium at a different membrane potential value. All right, so thinking about our two forces acting on sodium, there's a chemical force moving it in, there's an initial electrical force moving it out. And I keep saying initial because initially the force starts out as being stronger as initially in due to the stronger chemical force. But we want to think about how the electrical force continues to increase, okay? Continues to increase. So now we can put both of our ions together, right? Now we can put both of our ions together. So just recapping here, the chemical force for both ions, for sodium, it was in, for potassium, it was out, right? Now we're adding both the ions together, and that's why I keep saying sodium's initial movement is going to be in, but we want to think about bringing both ions into the picture, and we're going to see that that's going to change. So we're thinking about the chemical force for both ions. For sodium, it wants to go into the cell because it's higher concentration outside. For potassium, it's the opposite because it is higher concentration inside. Now, as we see both of our ions starting to move, we also want to take into account that the membrane is more permeable for potassium. So potassium has more of an opportunity to leave the cell according to its CDF than sodium can enter the cell according to its CDF. And that is reflected here in the number of channels that we see on this cell membrane. So potassium being at a greater permeability, we are seeing 3 ion channels here. Sodium is at a smaller or lesser permeability, so we're seeing 1 ion channel. So what this means is that more potassium can leave the cell than sodium can come in. So as you would imagine, that is going to create a more negative environment inside the cell because the cell can lose more positive charge faster than it can actually accept or have a more positive charge enter the cell. So that's the chemical force. Now let's add to the picture the electrical force of both ions. So the electrical force of sodium is going to be into the cell, right? We can see the electrical force here for sodium. Now we have a negative environment inside the cell. We have an electrical force wanting to move it in. And same thing for potassium. Potassium is also positively charged. Inside of the cell is more negative. We have an inward force, an inward electrical force for potassium as well. Okay, I want to kind of pause here and see what questions we have now that we've kind of put all the ions together. So they have a chemical force for sodium into the cell or potassium out of the cell. But because potassium has a greater permeability, more positive charge can leave than what positive charge can come in. So the inside of the cell becomes more negative. So now when we add the electrical force into the picture, both of our ions want to get into this negative charged environment. Okay, any questions so far? Okay. Okay. Now, when we think about both of the overall movement, for potassium, it has a strong force out and a weak force in. Okay, it has a strong force out and a weak force in. So the overall direction of potassium's movement is going to be out of the cell, but it's going to be very, very weak because we have an unopposed electrical force moving it in the opposite direction. So the overall direction is out. The overall magnitude is going to be chemical, subtract electrical, which is weak. Okay, so there's going to be an outflow, but a slow outflow for potassium. Alternatively, for sodium, sodium is great. Sodium has a chemical force moving it in, an electrical force also moving it in. So we just combine those two forces, right? When you think about their combined ECDF. So potassium is going to have a direction inward, because that's the overall direction of both forces. And the magnitude of that is going to be very strong. It's going to be a strong current rushing sodium into the cell because both forces are acting in the same direction. And we simply sum those forces, which is going to be a stronger magnitude. So sodium is going to have an inflow that is fast, right? A fast or swift rush of sodium in the direction into the cell, right? And so that is how we establish our resting membrane potential. We're going to end up seeing a steady state develop. And the reason that we have a steady state develop is because the sodium potassium pump is on the membrane as well. Although we're not including it in this discussion, it's still on the membrane and it is balancing the movement through the ion channels. That is to say that as potassium trickles out of the cell, the sodium potassium pump pumps it back in. As sodium rushes into the cell, the sodium potassium pump pumps it back out, okay? And the number of potassium and sodium that is moving according to the sodium potassium pump is also a direct reflection of that as well. So potassium is moving out of the cell at a weak force and 2 potassiums are being pumped back in. Sodium is moving into the cell at a strong force and 3 sodiums are being pumped back out. So eventually we establish this steady state where there's no longer a net accumulation of our ions on either side of the membrane. It's just a continuous movement with pumping the ions in one direction and leaking the ions in the opposite direction. And when we put a voltmeter into the cell, when it has achieved this steady state, the reading that we get is -70. And that is how we come to establish our resting membrane potential at -70 millivolts. Okay, all right. Again, I'm going to pause here and see what questions we have and basically how we describe this and how we've come to establish the resting membrane potential. Any questions at this time? Okay. All right, now I think we've said quite a bit for today. I don't want to go any further. What we're going to come back and describe when we pick this up, again, I'm going to share this on Monday, but what we're going to do at this point is think about how can we go from a resting cell at -70, and how can we think about some other channels that are in the membrane? So these are only leak channels for sodium and potassium, but there are other types of channels that we've described, such as gated channels, channels that are going to open up when the membrane potential moves from -70. We're going to call them ligand-gated channels or membrane potential gated channels as well. So when we think about that, that is going to allow us to move our ions and excite these cells, which is how we are going to be able to send signals from neurons to other types of cells. So we have only talked about how we establish this resting value, but we're going to move on to talk about how we can excite the cell based upon this resting value. Okay.